Some people have been asking me how we might, or how I might help them design the mechanical system for their pools in the studio project this semester. Uh, Complete disclaimer, I know nothing about pools, and so I'm just trying to help in any way I can. Somebody gave me this Natatorium design guide. Natatorium is a pool that one of your studio professors provided. It's a pretty nice document. I did a little bit of research on it. It's just summarizing ASHRAE 90.1 pool specifications, but this is but it's packaging things in a real world context, so it's a cool document. But then what I did by looking at this and looking at 90.1, I decided what I thought were things that we could use to do our best to model an HVAC system in an envelope that be would set our pool apart from other zones. So, and I have created templates in Climate Studio that reflect what I learned. So let's just go over those. First, I created a pool, a single zone pool. So just by itself, I'm just trying to make something that I can apply these templates to and just get some understanding of how it works. I gave it a 0.4 window to wall ratio. The sizing is based on me looking this up briefly or quickly. I then created a couple of templates. If you haven't done that before, let me show you how to do it. You go to this library book up here in the thermal analysis tab. Just pick any existing template, copy it, rename it to whatever you want to call it. I'm not going to do that because I've already done it. And whatever you've created will show up at the bottom. So I have a Natatorium zone space use template. Let's look at the settings I've chosen. So first off, in the loads, remember this is what we're adding heat to the space with these. One load we have is people. How would we? So in the document, basically it says that people in the pool are not adding heat to the space because they're in the pool, they're in the water, they're not in the air. And so this is based on the specification. So we just need to think about the people on the deck. So if we look up if we go to the code and go to the egress chapter 10 and look up swimming pool decks, we get a gross 15 square foot gross per person. And in Climate Studio it does the opposite. It's not square feet per person, it's people per square foot. Not quite sure why I have 09 there. I think it's just because that was the default and it was close enough. The way I thought about this was I said, okay, I took if I take 1 divided, oh, here it is, I already just did it. 1 divided by 15, I get 0.067. So that would be the people per square foot based on this 15% net. But that's not, we have to figure out what percentage of our pool is actually deck because the pool itself is not going to be adding the load from people. So I think I was going to divide it by 10 and make this 0.0067, I guess. But you can think that through on your own. I didn't change the metabolic rate. The document has a discussion about metabolic rates, but it's really not talking about in terms of heat load added to the space, I don't think. But the point is that the higher this number, the more active people are. If you wanted to change this, you could. First of all, I don't think it's going to have a huge effect, and secondly, since we're not talking about the people in the pool, I don't think it's really. I think people walking around on the deck would be 1.2 would be fine. I also created my own schedules. The way you do that is the same method. You come to the schedules templates in that same library drop down or dialog and pick any schedule you want to, copy it. I did that and created a pool schedule. If I edit that, we'll see that it is basically, I'm saying the pool opens at 7, it closes at 9, everything's on during that whole time, except for HVAC, for example, will be controlled by set points. And if you want to set your own, I had to create a custom schedule for that. To do that, I had to Um, come to the day schedules. Again, copy one. The way this works, I'll just show you the one I did, is so I made 7 a.m. to 9 p.m. If I edit it here, you can do things in a more complicated fashion. Go look at schedules; they're interesting, and they like for example, sometimes you might say, well, the HVAC is going to start slowly ramping up at 4 in the morning, and about to 40%, and then by the time people get in, it's full, and then at lunch it goes down a little bit. There's you can make this more complicated, but I just said everything's on between 7 in the morning and 9 at night, and you do that by just change. So then I'm saying it's full, 0 is off, 1 is full capacity. So I created my own schedules, and come back to the pool. Actually, I didn't set this one here correctly, so let me do that. The equipment and lighting power densities are pretty low, but that's coming from the standard, and that makes some sense to me. I set a luminance target of 45, which is also based on what I read in the standard and also in this guide. I'm turning off the hot water. For conditioning, this is something that's quite a bit different. First off, in a pool, and this makes sense, our set points are very different. Like I think that our typical set points that I've been saying we should be using, just as a rule of thumb, would be 65 to 68 for heating and 75 to 78 for cooling. Here we have a much higher heating set point. So we're saying even when it's cold outside, we're setting this at 82, but when it's I'm sorry, yeah, and then when it's hot outside, we're only setting it to 85. And if you think it through, that kind of makes sense for a pool, but that's different than other zones will have. We have to ventilate the space. I'm going to make it that it's 7.5 per people. That's just based on our NYC energy code typical setting. But this is different. According to what I'm reading, and this makes sense for a pool too, we have a lot more fresh air ventilation for the building. So the way this works is you have to have fresh air ventilation for the number of people because they have to breathe, but you also need to have ventilation based on the size of the building and for different uses, how much you need to flush it out in terms of if there's off-gassing and other pollutants inside. So there's two different numbers, and this is very high, like 0.06 would be what we were doing as a baseline for NYC. So we're going to have a lot more heat loss because of this ventilation that's specific to a pool. So that's another way that we're going to have a difference with this zone. Okay, so that's the space use template. Then I did create a construction template. The basic idea here is kind of common sense, well, maybe at least to me. We need to use materials that are resistant to water, and so I did a mass roof with it's concrete with insulation on top of it. I also have a mass wall, so I'm looking at thinking about concrete or concrete block or something like that. I have a very low infiltration rate. This is definitely passive house level. It'd be hard to do. You need good professionals to do it, but we don't want air leakage in the space because we don't want humidity pushing through into the other parts of the building. We also, by the standard, and it's talked about in the guide, we also would want a negative pressure in the pool. In other words, we want to have it to where the humidity is not pushing out into the rest of the building. It's actually being pushed in to the pool. We have no way to really set that in this simulation workflow that we're using. But air tightness at this level will be a good approximation of that, or would be helpful to that. Okay, then I set my exterior windows to be very energy efficient, and partly because that's going to help with, they'll also be very watertight. So if you want to do the same thing I did, I would pick, if you click on these, on the columns, it organizes in in chronological order or number order, and so I picked this setting. This assembly, triple pane glass, which has a very low U value, 0.1, so it's like an R10. A low solar heat gain coefficient and a low visibility. Just that's not that's pretty high actually for something that's energy efficient. Anyway, that's one I picked, and so that's our envelope that's matching the pool requirements. Then the final area that we can consider is the mechanical system. One thing that is mentioned that's pretty cool in this document, and there's a lot of stuff in here that you can look at in terms of that we've talked about. So this is a great, and I think these diagrams are really clear. So this is a good application of things we talked about in other classes. Like one thing that you could design but not really model is the idea that they're because of the, well, just read this, because of the particular demands of heating and cooling in the pool space, they're suggesting having an air flush over the windows in certain situations. That's not uncommon as a strategy. As we're getting more energy efficient buildings that have higher mean radiant temperatures, we don't need to do that as often, at least conceptually. So anyway, there's things that we would not be modeling in our simulation that you might want to consider from this document. And if you don't have it, I can supply it to you. But I think that you've been given to it by, hopefully all the professors have given something like this. But no, what I was looking for is this. So there's a huge humidity load in a pool. Makes sense. It's mostly water in there, right? So that's continually giving off water vapor to the air. And so in this document, it talks about a specific dehumidification system. But when I say specific, what it's doing, what this little diagram is showing, is that it's designed to take the latent heat, the humidity, out of the air. And so now we're, unlike a swamp cooler where we're taking hot, dry air and wetting it by like blowing it across, dripping water or something like that, and then we're going to lower the temperature of the air but raise the relative humidity. Here we're doing the opposite. We're going to reduce the relative humidity to dry the air, and then that's gonna pull heat out. We'll have the latent heat energy available that we can then use to heat the pool. Because even in the summer, we're probably going to be heating this pool. So this is a very efficient way of you're killing two birds with one stone. You're getting your dehumidification, and you're also getting pool heating. And so it says in this document that it's a typical system would have a COP of 8, which is very high. So it's almost like you're getting free pool heating by dehumidifying the air. But that's not something we can really model in our system. It's a completely separate dehumidifier. But what we can do is there's in the specifications it says that we want to set our humidity range between 50 and 60. So you remember I brought down a VAV. Remember, you just open these and bring them in. I'm going to delete this one now when it comes in. Oh, it's just the same one I've already got. But you can bring in multiple. You can bring in as many of these mechanical systems as you want. So I brought a VAV system in. We may want to try something different. I don't know, but that's the one that kind of I bet would be the default here. And I then edited it to, and actually I decided to make it as efficient as I could. And for a pool with a big load like this, I think in a fairly big footprint, maybe we could do ground source heat pump piping underneath the pool. I don't know. So I decided to make that my heating and cooling, my source of heating and cooling. But then in the air loop where I have heating or energy recovery ventilation, we've talked about this. You may not understand it yet completely. Heat recovery, actually here it just says it. Usually when we say heat recovery ventilation, we're talking about sensible heat. And if we say energy recovery ventilation, it's something that does both. But what they're doing is separating them out here. And I have set a typical heat recovery ventilation amount, but I've set the latent energy recovery to 0 because in the code it's saying that we don't, or in the specifications that we do not want to be ever bringing in extra humidity, which could happen at certain times of year with energy recovery ventilation. So that's why this is 0. This 0.7 means that 70% of the heat that that's in the air that we are, well, if it's cold outside and we're bringing in fresh air and we're taking our nice warm air inside and exchanging it with that fresh air, we are also exchanging 70% of the heat with this. So we could go higher than that 70. That's a pretty conservative. There's equipment that will go higher, but that's what I'm going to leave it at. But this is the big one that I changed. So the typical, this could be off in your, I don't know what you've been using, but the typical default here is 20 to 80%, and that's basically the comfort zone. We say that we can, I mean, 20 is really low, but that would, that you would not be in danger, at least if you were in that zone. What the code is saying is that we should bring this up, or not the code, the 90.1 guidelines. We should keep the humidity between 50 and 60%. So you'll see that's going to change things quite a bit. Also, that's very different than what other zones would be. And so, like I say, we could do what we've just done here with, we could try a VRV system. We could do whatever we want, but we would want to make these same adjustments to the energy recovery if we had a different mechanical system. And so what I've done then here is I've set up custom templates for the pool that for space use, for construction, and for a mechanical system that allow me to differentiate it from other zones. So I feel like that's a pretty good for the level at which we're at, at this point in your careers. That's a pretty good. That's good enough, I think, to consider the HVAC for the pool. If a professor or somebody else has other suggestions that we could try to model, please let me know. We'll see if we can do it. So then I ran a test, and looks very different right off the bat, right? So we have heating and cooling every month, and this light blue is the humidity. So it's because we set that humidity so high. We have really high humidity. I mean, not so high. It's such a small range. We have a very high energy load to remove or to keep that humidity at that range. So we have a lot of equipment loads here because of that also. Anyway, and then so that we can look at the peak heating and cooling loads to try to choose equipment for this zone. And of course, it's going to be, I've got a lot of windows in this. It's going to be different when you have it connected to your actual project. But I think that this is successful also because just running this one in this one quick iteration, it's a very different zone than what I'm used to seeing for other types of occupation. I mean, or space use. Okay, so we can work on this in class and talk about it more, but I wanted to just get this out in a form that gave you the benefit of what I learned from looking at pool mechanical systems very briefly. Hope it helps.